Welcome to Podcast Learn and Fun. Let's start today's journey of learning. Today, we're going to explore a concept that sounds simple but has these mind-blowing consequences, the idea of phase in quantum physics. It's funny how, the things we can't see directly can have such a huge impact on the universe.
It really is fascinating. You're right, we often think about waves, in a very visual way, like waves crashing on the shore. But in quantum mechanics, waves describe the behavior of these tiny particles, like electrons. And just like those ocean waves, these quantum waves have phases which tell us not just where the wave is, but how it's moving and interacting.
So it's not just about the wave's position, but also it's like vibe, so to speak. Like, is it going up, down, or somewhere in between?
That's a great way to put it. And the thing is, this vibe, this phase, plays a crucial role in how quantum particles interact with each other. One of the clearest examples of this is the famous double-slit experiment. You shine a beam of light through two tiny slits, and instead of seeing two bright spots on a screen behind it, you get an interference pattern, these bands of light and dark.
Oh, I've always found that experiment so bizarre. It's like the light is somehow interfering with itself, creating this pattern out of thin air.
Exactly. And that pattern is a direct result of the phases of the light waves interacting. When the waves are in sync, their peaks and troughs line up, they amplify each other, and you get a bright band. But when they're out of sync, they cancel each other out, and you get a dark band.
It's like two waves colliding. Sometimes they make a bigger wave, and sometimes they just fizzle out.
Precisely. But here's where it gets even more mind-blowing. This concept of phase is absolutely central to one of the weirdest phenomena in quantum mechanics: entanglement. You see, when two particles become entangled, their fates are linked no matter how far apart they are. It's as though they're sharing a secret code, and that code is written in their phases.
Okay, now you're really making my head spin. So the way these entangled particles communicate is through their phases.
You got it. The phase difference between entangled particles dictates how their measurements are correlated. It's like having a remote control for the quantum world. Change the phase, and you change the outcomes of experiments.
So this phase isn't just some theoretical mumbo-jumbo. It has real measurable effects on the behavior of these entangled particles.
Absolutely. And to make things even more interesting, there are different ways to look at these quantum states, different perspectives, so to speak. One of them is called the Hadamard basis.
Okay, so it's like looking at the same object from different angles, to get a more complete picture.
Exactly. Think of it as shifting your perspective to gain a deeper understanding of how phases influence these entangled systems. And what's fascinating is this isn't just some esoteric mathematical concept. The control we have over phase is what underpins many emerging quantum technologies.
You mean like quantum computers and all that futuristic stuff?
Precisely. Technologies like quantum teleportation and cryptography rely heavily on manipulating the phase of entangled particles. It's like using the phase as a key to unlock these incredible quantum possibilities. But there's even more to it than that.
Okay, I'm on the edge of my seat. Tell me more. What else can you do with this phase key?
Well, there's this phenomenon called the Aharonov-Bohm effect, which demonstrates just how strange and counterintuitive the quantum world can be. Imagine a charged particle moving along a path. Now, imagine there's a magnetic field tucked away in a region that the particle never even enters.
Okay, so the particle and the magnetic field are completely separate. They never interact directly.
That's right. But here's the kicker. The particle is still affected by the magnetic field, even though it never comes into contact with it.
Wait, what? That doesn't make any sense. It's like some kind of spooky action at a distance.
It really is mind-boggling. And guess what plays a crucial role in this bizarre effect?
I'm betting it's our mysterious friend, the phase.
You got it. The Aharonov-Bohm effect is a prime example of how phase, this seemingly simple concept, can lead to truly mind-bending phenomena in the quantum world.
Wow, that's incredible. It really makes you wonder what else is out there lurking beneath the surface of our everyday reality.
It's a reminder that the universe is full of surprises, and sometimes the most profound insights come from the things we can't see directly.
So we've been talking about how this invisible thing, this phase, can have these crazy effects on particles. But how does that translate into actual technology? You mentioned quantum teleportation earlier. Is that really a thing, or is it just science fiction?
It's definitely not science fiction. Quantum teleportation is a real phenomenon, and it relies heavily on the manipulation of phases, but it's not quite like beaming someone up to a spaceship like you see in the movies.
Okay, so what is it exactly? What are we actually teleporting?
What we're teleporting is information, not matter. It's about transferring the quantum state of a particle from one location to another without physically moving the particle itself.
So it's like sending a blueprint that allows someone to recreate the particle at a different location.
That's a good analogy. And the way we transmit that blueprint is through entangled particles and the manipulation of their phases.
Okay, that's starting to make sense. So where does the phase come into play?
Well, imagine you have two entangled particles, one at point A and the other at point B. Now you want to transfer the quantum state of a third particle, let's call it particle C, to point B.
So we want particle C to essentially become a copy of particle B, even though they're in different places.
Exactly. And to do that, we perform a series of operations on particles A and C, carefully manipulating their phases. This creates a special kind of correlation between them.
Okay, and then what happens? How does the information get from A to B?
Here's the wild part. We make a measurement on particles A and C, which instantly affects the state of particle B, even though it's far away. The information about particle C's state is encoded in the measurement outcomes, which are dictated by the phases of A and C.
So it's like the measurement on A and C is sending a signal to particle B, telling it how to reconfigure itself.
You got it. And by manipulating the phases just right, we can ensure that particle B takes on the exact quantum state of particle C, effectively teleporting the information from one place to another.
That's mind-blowing. It really challenges our whole notion of what it means for something to be here or there.
It definitely highlights the strange and non-local nature of quantum mechanics.
So we've talked about teleportation, but you also mentioned that this phase stuff is important for cryptography. How does that work?
Well, you see, traditional cryptography relies on the difficulty of factoring large numbers, but with the advent of quantum computers, those codes could easily be broken.
Right. I've heard that quantum computers could crack even the most secure encryption algorithms we have today. So how does quantum cryptography offer a solution?
Quantum cryptography utilizes the principles of quantum mechanics, including phase, to create codes that are essentially unbreakable. One of the key ideas is that any attempt to eavesdrop on a quantum communication channel will inevitably disturb the system, alerting the sender and receiver.
So it's like a built-in alarm system that goes off if someone tries to snoop on the message?
Exactly. It's based on the fundamental principle that you can't measure a quantum system without altering its state.
Okay, so how does phase fit into all of this?
One way to implement quantum cryptography is by using the polarization of photons, which is directly related to their phase. You can think of polarization as the direction in which the light wave oscillates.
So we can use the phase of photons to encode information.
Precisely. By sending a stream of photons with different polarizations, we can encode a secret message. And because any attempt to measure the polarization will disturb the system, we can guarantee the security of the communication.
That's incredible. So this phase, this seemingly abstract concept, could be the key to creating truly unbreakable codes.
That's the idea. Quantum cryptography is still in its early stages of development, but it holds immense promise for securing communications in the future.
It seems like the more we learn about this phase stuff, the more we realize just how powerful and versatile it is. Are there any other areas where manipulating phases is opening up new possibilities?
Yeah, it's amazing to think that something as seemingly simple as the phase of a wave, could have such profound implications for the future technology.
It really speaks to the power of quantum mechanics and how it's, changing our understanding of the universe, and the applications go far beyond cryptography and teleportation.
Okay, you've got me intrigued. What else is this phase key unlocking?
Well, one of the most exciting areas of quantum computing. You see, traditional computers use bits, which can be either 0 or 1. But quantum computers use qubits, which can be in a superposition of states, meaning they can be both 0 and 1 at the same time.
Right. Yeah, I've heard about that. It's like they can explore multiple possibilities simultaneously, making them exponentially faster for certain tasks. Exactly. And the key to manipulating these qubits and performing these complex calculations lies in controlling their phases. By carefully adjusting the phases of individual qubits, we can create interference patterns that allow us to solve problems that would be impossible for classical computers.
So it's like orchestrating a symphony of phases to perform these mind-boggling computation.
And that's a great analogy. It's like conducting an orchestra of quantum waves where the phase of each wave determines the outcome of the performance.
This is incredible. It sounds like understanding and manipulating phases is essential for unlocking the full potential of quantum computing.
Absolutely. It's one of the fundamental challenges in building these practical quantum computers, and researchers are developing these ingenious techniques to control these phases with incredible precision.
It's exciting to think about what the future holds as we continue to explore the mysteries of the quantum world. Who knows what other amazing discoveries await us as we delve deeper into this realm of phases and entanglement.
It's a journey of endless possibilities, and I'm sure there will be many more surprises along the way. The more we learn about the quantum world, the more we realize how much we still don't know, and that's what makes it so fascinating.
Well, for one, I'm eager to see where this journey takes us. It's been an incredible exploration of the power and mystery of quantum phases. And it's clear that this invisible force is shaping the future of technology and our understanding of the universe.
It's been a pleasure sharing this journey with you, and I hope it sparked a sense of wonder and curiosity about the quantum world.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.